We want to just know how much energy is involved, and we want, because heat, like we say heat of reaction is not a state function. Heat of reaction is a path-dependent function, unless you make it a state function. You can make it a state function by calling it either the enthalpy or the internal energy change, QV or QP. Well, these are actually delta H's, so this should be enthalpies of combustion. Then we know it's a state function, and therefore we always know we're going to get the same amount of heat per gram. And so these are all per gram amounts. And so if you look at it, which one gives us the most energy per gram? Natural gas. Natural gas is excellent fuel. I mean, you look at the oxidation state of carbon in natural gas, -4, so it can go from -4 to +4. That's 8 electrons per carbon atom. And so it's quite a good fuel. It's quite electron rich. Not only that, natural gas burns very clean. Some of these other ones, you end up getting some unwanted byproducts like coal, if there's sulfur in the coal. Although coal technology, combustion of coal has come a long way. Now they have scrubbers. So, all this acid rain stuff that was a big deal in the past isn't such a big deal anymore because they just scrub the exhaust. That is, they just clean the exhaust out of these oxides of sulfur. Isooctane, there's something called the octane rating of gasoline. It's like going to be 87 or 89 or 91. That's usually based on how octane burns. Gasoline, they don't want to burn too fast, otherwise it causes detonation in the car, which could damage things. And they don't want it to burn too slow, and so they adjust it, the mixture, so it burns nicely there. But gasoline's also, hydrogen's up there as well, except hydrogen's a gas, and so it's hard to store. But if we switch to methanol or ethanol, a lot of people are thinking about using a lot of ethanol in their gasoline. They have, in California, they have E10, is it? E10 means 10% of your gasoline's ethanol, I think. Well, some gas stations have E85, but you can't use E85 unless your engine is tuned for it, because E85 doesn't have as much kilojoules per gram, so you have to use a lot more fuel when you use E85. And so you have to have different fuel pumps and that kind of stuff so you can get more. And then you can also burn waste, municipal waste. I remember my friend went to apply for a job at Hyperion over here, and during the interview he got asked a question. The question was, is waste, the sludge we collect here, is it a reducer or is it an oxidizer? And he's applying for a chemistry job over there. He just graduated with a bachelor's, and I thought, oh yeah, it's a reducer. But he said, oh, that was a ridiculous question because it's neither. But I was thinking, waste sludge should be a reducer. It should be burnable. But then I thought, okay, he was a student of mine, so he didn't quite get it. The whole oxidation reduction stuff.
How do you synthesize natural gas?
How do you synthesize natural gas? There are different ways. Like, for example, Hawaii, it's too expensive to ship natural gas there. So what they do is they take, for the oil refineries, they have oil refineries in Hawaii. So they take the oil that they're going to use to make fuel or something like that, and then they crack some. And in the process of cracking is breaking the bonds. And when they break some of the bonds, methane is byproduct, and so they use that as their natural gas. But most of the gas in Hawaii is not natural gas. Most of it's propane, so you have to go around and fill up the propane tanks. Like in certain cities there, they're only, like on Oahu, there's only propane. Only in Waikiki is their natural gas. They don't have the infrastructure there, so they don't have the pipes to pipe it around. So people end up filling their propane tanks. So you use a propane stove. I don't know if you've used a propane stove, but propane doesn't burn as clean as natural gas. There's a little bit of residue on there. So some people on, I was reading this, some people on boats, they want to switch their boat to having a natural gas stove rather than a propane stove, but natural gas doesn't pack the density that you get in propane because you could liquefy the propane in the tank so that you can carry more of it, so it just doesn't last as long. They're natural gas vehicles. And so I was interested in natural gas vehicles. These natural gas vehicles are vehicles that just burn natural gas. There's two types of natural gas vehicles. One type of natural gas vehicles converts the natural gas into electricity, so you get electrical work. Another one is just burns it in a regular gasoline engine. So I was looking at the one that burns it in regular gasoline because, like the buses, you know, the CNG buses, you know, I used to hate following buses because there's so much diesel fumes, and I hate diesel fumes. And so there's lots of NOx and other things that aren't good for your health. And so diesels are really gross polluters. But anyway, these buses that burn CNG are fine. I don't mind following them. I could have, you know, the vent to the outside. I always turn it on recirculation if I'm following a diesel.
The negative side will turn off the kilojoules per gram, meaning that it's like an exothermic reaction.
All these are exothermic reactions, so the surroundings are going to benefit. And we need the surroundings to benefit because the surroundings are going to use this energy. This is, you know, this is heat. And there's I had this student who was always talking about, you know, have you ever heard of the Carnot cycle? Heat engines, that kind of stuff. They're getting confused because we don't have to convert this energy into heat. Remember, delta H is the net energy that you get. And so what we can do is we can take that chemical potential energy, and rather than converting it all into heat, which is this, we can use that chemical potential energy and convert it into work. Unfortunately, we can't convert it into work with 100% efficiency because there's friction and other stuff that's going to sap away energy. So we're going to lose some as heat, inevitably, but this doesn't have to be heat. This is the net energy after all the taxes. Maybe there's no tax, or maybe there's a bonus. You know, this is your take home. What would you rather know? Like for example, you know, if you buy a car or you buy something, you know, if you buy a car, they're gonna just tax you based on your home zip code. And so you know what the tax is going to be because it's going to be your home zip code tax or wherever the car is registered. But if you go to the store, you know, for example, I bought some stuff in Gardena and I bought some stuff in Torrance. Well, Gardena is more expensive because the tax there was more, you know. And the tax is different depending on what municipality you're in. And Gardena has like over 10%, Torrance has under 10% tax. And so it's hard to predict sometimes because I don't know what the taxes are and I don't follow what the taxes are. Because if I went to Hawthorne or Lawndale, what are the taxes there? You know, it's a pain to keep track of that. Well, the tax is inevitable. I mean, you got to pay the tax. You can't get around it. And so this is the same thing. You got to pay the tax. So what we want to know is how much is it going to cost you out of your pocket, you know, or how much are you going to get? And this is the amount that we're going to get. Whereas delta U is the gross. So you might buy a $10 item in Torrance and a $10 item in Gardena, and it's going to cost you different amounts. And so that's a pain. That's delta U. So this is why we want delta H. And this delta H, this is the enthalpy. So this enthalpy is the amount of usable energy that we can, and then we can use this energy to do work. So for natural gas, we don't want to burn it and just convert it into heat unless you're heating a pot of water. If you're heating a pot of water, then yes. But if you're trying to drive a bus, no. If you're trying to drive a bus, you want it all mechanical work, you know, as much as possible and the minimal amount of heat. Natural gas burns very clean and very efficiently. It's quite good. So natural gas, the only problem is that what people complain about is the CO2 emissions. So this is why there's a big push. There's a big push to get rid of natural gas stoves inside that. Restaurants first, so it was banned. Natural gas, and then large complexes, and then eventually they want to ban natural gas stoves in houses. So that's the plan, I think. But, you know, right now it's kind of weird because if you switch from natural gas to electric appliances, how is most electricity made? Most electricity is made by burning natural gas to drive generators to generate the electricity. So something has to be done more at the origin of that. And then electrical, I mean, electrical is great for many applications, but for some, like if you have like a walk, like Panda Express or something, and they need these very high temperatures, that could be difficult. But anyway, natural gas is an excellent fuel. So these, they say, are non-renewable resources, but people are trying to make synthetic fuels from different things. So they grow corn. From the corn, they get ethanol. You know, you ferment the corn. And from the ethanol, then you can get either burn that straight, or you can process that further to make other fuels. So synthetic methane comes from other fossil fuels, but synthetic methane from, let's say, non-fossil fuel sources, that would be more of a challenge, and I don't think anybody's quite done that, because it would probably take more energy to make it than you get out of it. But I don't, you know, the whole infrastructure is here. So I think they need to give more time to transition to full electric infrastructure, whoever's dictating these. But anyway, if we look at the energy consumption by source, we can see, actually this is not, I don't have the legend here, actually, so let me skip this. Well, what people are worried about when burning fossil fuels is the greenhouse effect. You know, there are certain greenhouse molecules. These greenhouse molecules have certain vibrations that they absorb infrared radiation. Oddly enough, like the nitrogen in this room, when we look at the vibrations of the nitrogen and the oxygen in this room, the atoms are vibrating. However, those do not absorb in the infrared. Those are not greenhouse gases. So the nitrogen and the oxygen in this room are not greenhouse, but the room does heat up. The room heats up. You know, if there's sun shining through a window, the room's going to heat up. Well, that's primarily due to, like, you know, water vapor. Water vapor is an excellent greenhouse gas. So as the humidity goes up, so does this feeling of a hot room. But there's certain molecules that have vibrations that will trap in the heat, they say. And so it acts as a heat trap. And so you can experience the greenhouse effect, like in your car. If you have a car on a hot day and you go in, you know, it's going to be quite hot. It traps in the heat, which is, of course, bad for pets or whatever else, children that are left in the cars, because the interior temperature of the car, due to the greenhouse effect, is going to be much higher than outside the car. But what happens is, let's say, light, this squiggly line, this wave is light. And so we have this visible light coming in, and the visible light gets absorbed, and some of the light is radiated. Infrared is light as well. But you can't see it, but you know, you can feel the heat. If you put your hand, that's an easy way of detecting infrared. And so some of this visible light comes in, some infrared light also comes in. But it gets absorbed, and sometimes it'll get re-emitted as infrared, and this infrared gets trapped inside here. They're greenhouse gases here, especially. And so the greenhouse gases, one of the ones that people are looking at is methane. Methane has a tetrahedral shape, and it has all these vibrational modes, we call it. And so a lot of people are worried about methane, as well as CO2. Methane's a more efficient greenhouse gas, better at trapping in the heat. Water is a very efficient greenhouse gas as well.
So is it the way that the molecules vibrate that make them trap in the heat?
You're right. It's the way the molecules vibrate that makes them trap in the heat. And those are dictated, we can look at the theory of those vibrations later. But anyway, so things like methane, water, CO2 are excellent greenhouse gases because of the way they vibrate that traps in the heat. And therefore people are looking, you know, about CO2. They're looking at ways of reducing the CO2. You know, on the space station, there's ways, because if the CO2 concentration gets too high, could cause your blood pH to get too low. You know, from CO2 is an acid, and if your blood pH gets too low, then you could suffer from acidosis or even death. But the CO2 levels we're looking at here are quite a bit different. I mean, CO2 is part of the percentage of the atmosphere is very small. And so right now there's this. But so people are looking at ways of reducing CO2, like banning natural gas stoves, banning cars, driving all electric. If the electricity is produced by nuclear, then yeah, maybe the whole infrastructure can change. But I'll tell you, sometimes if you don't have a charger at home, then sometimes it's hard to find a charger. Like one time I was almost out of charge, and all the stations around were full. And sometimes you have to wait. It takes, some people sit there for like an hour, 2 hours at the charging station. Sometimes you have to wait a long time to charge. I think the longest I had to wait was 40 minutes. I waited in line to charge, and then the charging itself, I probably charged it for about an hour. So an hour and 40 minutes, something like that. So they need to build more charging stations, and that would help. But, modeling the atmosphere is not so easy. And so, the best thing is to look at the data. When you look at the data and see what makes sense to you. Is the emissions from cows so significant that it's going to really make a meaningful impact? I don't know. And so one of the proposals is to, I don't eliminate cows, but eliminating cows just seems too extreme to to kill off a whole, what they call it in biology. But anyway, so they're chemists. You know what they're chemists doing right now? They're looking at additives that they can put in cow feed to reduce their methane emissions. So, these are like the over-the-counter things that you can get, whatever. And so they just put that in the cow feed, and hopefully it reduces their emissions enough that they don't have to eliminate the cows somehow. But I may be taking their policies too extreme. But anyway, this is the big one of the big issues, and this is impacting things, because I think this is one of the reasons why a lot of people want to see gasoline and gasoline stations go away, because they're worried about this global warming. But the models, are all the predictions. What you want to see is how accurate are the models, or the observations. So these are the observations here. The CO2 concentration has been monitored since 1960 to 2010. So we're going from 320 parts per million to 380 parts per million. So what kind of impact does that have on temperature? So they're trying to correlate it with global average temperatures here. But still, these things are not. When we look at this data, we want to know certain things when we do statistical analysis of these, like R squared. Are there other factors involved in this? Historic data. And so what we do is we try to do this scientifically. There should be a good, vigorous scientific debate. And so if and this is the way science is supposed to work. There should be climate deniers, and there should be climate, global warming proponents, and they should get together, and then they should, argue with each other. But all too often, what they want to do is they want to censor one side or censor the other side. That's not good in science. Censorship is the worst thing you can do in science, I think. What people should decide is which side to support based on argument, not on censorship.
Last time I read an article, they were making comparison between both, and then yet the tycoons, which is the most powerful, whales, they're controlling the final, I would say, the final these
He-
kind of problems.
yeah,
Atmosphere,
you know,
global warming and all these kinds of stuff.
what I like to hear, because what I hear all too much of is, there are anti-science climate deniers. I'd rather hear something like, well, their argument is weak because of this, this, and this, But I don't like to hear this so much talk about, all the scientists agree. Do all the scientists agree? I want to know, I want to know if there's disagreement and what their arguments were and the reason for discounting those arguments. Because sometimes what happens is that people get into groupthink and they don't see certain things. This has happened in the past where everybody's thinking the same, and then they miss certain things. There are examples of drugs that have this kind of groupthink and have some really negative effects down the road, or other things. And so we need a good open debate in science. So that's not something that's been happening so much recently. And so this is my own. In other words, politics should stay out of science. I mean, there shouldn't be any kind of political.
But the other group that you mentioned, they weren't there at all in the article. And well, I read that most of the scientists, they were agreeing on that. But it seems like the tiny few people, as if they are like sharing those kind of tycoons,
Yeah.
which is like they're going to affect the resources, their resources. This is why they wouldn't get any, kind of result.
Yeah. The controlling the message is important, but I don't know. It should be free exchange of information. That's what we should have.
Whatever they will affect them as a financial, they will.
Yeah.
So they care a lot for the money this is going.
Yeah. Unfortunately, it seems to be what's happening a lot. Well, let's take a look at these potential energy sources. People are trying to make gasoline from coal as well, as a starting point. But coal is a non-renewable resource. Methanol as well. Ethanol is renewable. It's fermentation. Biofuels. This is like used oil. But used oil doesn't burn so clean, like used cooking oil. And so a lot of people were trying to make biofuel cars with this. And then hydrogen. So right now, hydrogen is looked at as an alternative, because when you burn hydrogen, then you should just form water. And so hydrogen. Problem is hydrogen is relatively dangerous. Potential explosion hazard. Not only that is, how do you make the hydrogen? And so they have different kinds of hydrogen. They have like 5 or 6 different colors of hydrogen depending on how it's made. Now, there's some hydrogen that's made from like coal. And so they give that a lower rating than hydrogen that's made from, let's say, electrolysis of water.
What's that mean?
It's based on the carbon footprint of the hydrogen. And so right now, I think, what is it, purple hydrogen is the best? Let me look. Oh, maybe purple hydrogen is not the. It's one of these. Purple hydrogen is hydrogen produced through electrolysis powered by nuclear energy. So some people don't like nuclear energy probably for good reason. I mean, look at what happened at Fukushima and Chernobyl. And those were pretty huge disasters. But can it be done safely? Probably. And is it good? Yeah, it's not, nuclear power is not the most efficient, but it would be the cheapest, one of the cheapest sources of electricity. And then there's pink hydrogen or red hydrogen. I guess this is the same. And so we have the hydrogen color spectrum.
Does it hydrogen actually light up differently?
No, this is the exact same hydrogen. You can't tell the difference. Once you have pink hydrogen or purple hydrogen and green hydrogen, they're exactly the same. It's just H2. It's just how it's made. It's like the electricity. You know, we in California pay a premium to get green electricity, that is electricity produced from renewable sources, but there isn't enough producers. Like there aren't enough turbines, there aren't enough solar, there aren't enough dams generating hydroelectric electricity. So we pay a premium for green electricity, but we also pay a big penalty because most of the electricity we use is not from green, it's from combustion of natural gas. And so it's going to take time, but anyway.
That means the hydrogen is still like looks perfect.
Hydrogen, the cost of hydrogen skyrocketed. There are people who are complaining a lot about, and there's lawsuits against like Toyota right now because the price of hydrogen has skyrocketed. So they're suing Toyota because of something. I don't know why. But Toyota had a hydrogen powered car. I drove it. Did I tell you I drove their hydrogen powered car? Yeah. I was scared if somebody crashed into me, it might explode, but maybe I'm going to get more comfortable with it because apparently they could build tanks that can hold hydrogen that can withstand extreme accidents. But you work with compressed gases, and when you work with compressed gases, you have to go through a safety course because what can happen is if the valve gets knocked off or if there's a leak, you have compressed gas at over 2,000 psi. And if there's a leak, what it does is it pushes all the air out of the room and you die through asphyxiation, you know. So the same thing could happen with hydrogen. You know, if there's a break there, then all the air in the room could be purged, even if there's no heat source to ignite it.
Does it absorb it? Absorb the air inside?
It doesn't absorb it, it pushes it out. It just forces it out. It'll mix, there's diffusion, but there's not enough time for the diffusion. So as the hydrogen or whatever gas comes out of the cylinder, it's coming out so fast, it's pushing all the air out of the room. And so it's a very big hazard. So you have to go through safety training and all this other stuff so you don't die. People have died due to that before. It's all part of OSHA. OSHA is this occupational safety thing. So green hydrogen is made using clean electricity. Well, clean electricity is made by using, this is what we pay for it, the clean electricity in California. This is why the electricity rates are quite high in California compared to other states, you know. Like on the Tesla says, okay, you know, you've saved this much in gasoline, but then you look at the electricity rate that they have programmed in the Tesla. The electricity rate they have programmed in the Tesla is 13 cents per kilowatt hour. But, you know, when you go to one of these stations out here, it's over 60 cents per kilowatt hour. So it's getting comparable to gasoline. To fill up the Tesla is getting about the same. But if you go to Nevada, you know, in Nevada, it's less than 20 cents per kilowatt hour last time I filled it. And so it's way cheaper. Anyway, getting back to this. Green hydrogen, and then they have blue hydrogen. Blue hydrogen is made from natural gas, and et cetera.
But asking like in the war model, like you said that the color that certain gases emitted had to do with energy levels. Do you remember? It was like
Certain gases are emitted because of what?
no, like the certain colors are.
Oh, certain colors are emitted? Yeah. Like in the flame, there, the blue color in the flame? Yeah.
But I thought it was like the example from the textbook was like it was hydrogen gas. Was it not hydrogen gas? The blue,
Oh, with a blue flame?
no, like the blue.
Purple flame? Yeah. It is. What happens is the color, it's not the color of the gas. The gas itself is colorless, but it's excited atoms. We're going to talk about that in the next chapter, actually. So we'll look at it. So how many different types of hydrogen? Green, blue, gray, black and brown, pink, turquoise, yellow, white. So, and this is all part of the hydrogen infrastructure. They're supposed, now I remember what the lawsuit. They're suing Toyota because there were supposed to be many, many hydrogen filling stations in California. But it turns out that there are just like a handful of hydrogen filling stations in California, so you're kind of locked in a small area. And then I think Toyota based it on, because I think the governor said that they were going to be building a lot of these hydrogen stations, but they never built any. So that's what happened. And so there's a bunch of lawsuits going on with hydrogen. But maybe with time hydrogen might be a viable source. But it's not going to happen in like 10 years. I think it's going to take a lot more time probably. But people should be looking at this, and people should be investigating such stuff for alternatives. Okay, the last part, this is a transition into Chem 1B. In Chem 1B, normally in Chem 1A, we want to go from higher energy to lower energy. That is, we want to go from stronger acid, stronger base, stronger oxidizer, stronger reducer, to weaker. And so stronger species are higher in energy, weaker species are lower in energy. That's typical. So this is a typical driving force in nature. However, there are some reactions that occur that go the opposite direction. There are reactions that occur that go from weaker to stronger. Why does that happen? And so we have to look at that. And why that happens is because of something called entropy. So we're going to also look at the entropy as a driving force too. And we look at the play between energy, that is enthalpy, since we're constant pressure universe. If we're constant volume, we'd look at the internal energy. And in constant pressure, we're looking at the enthalpy, because that's going to tell us the total energy, basically. Not the total internal energy, but the total energy that we're interested in. And so we look at spontaneous. What makes something spontaneous? Usually going down in energy makes it spontaneous, but not always. And so in Chem 1B, we look at these in more detail. And so both of these reactions are spontaneous. The rusting of iron here, that's minus 16, so we're dropping quite a bit in energy. But when you look at this one turns out to be spontaneous as well. And this one is, here. This is an exception to the solubility rules. Chlorides, bromides, and iodides are all soluble, but this one is a barium. Why would it be? So it's a rule, it's not a law. Ammonium chloride, well, this could be another reason. But there's maybe not that much water. If there's more water produced, maybe it should be aqueous here. Actually, this should be aqueous. There's just not enough water to make them aqueous. But anyway, this is a spontaneous reaction that's endothermic, so this actually goes up in energy here. It doesn't go up by a huge amount. I mean, when you look at this is almost 2,000 kilojoules. This is only 165, and this is the case we see. When we don't go up too high, it can happen, and it can happen due to something called entropy, which we'll talk about in Chem 1B. I'm not going to talk about it here. Just be aware of that. And so when we make these predictions, they're just predictions for reactivity. For sure, if it goes downhill, then yeah, that should happen. But we have to look at the entropy, because if it goes uphill a little bit, maybe it'll happen. If it goes uphill a lot, then it's not going to happen. If this was plus 2,000 kilojoules, forget it. It's too high of a hill to climb. But if it's a small hill, then it could happen. And so when we're looking at a driving force, all our driving forces were downhill, going down in energy. But there's other things we have to worry about too. This was in the PowerPoint slides for the reaction. Some spontaneous are very slow. They're so slow they never happen. Others are very fast. Some spontaneous processes are exothermic, others are endothermic. So it's harder to predict because we want to go downhill. Going downhill should be easy. So why are we going uphill? And the reason's entropy, and we'll talk about that later. So the example, the example calculations I was going to leave to the tutorials. That's why I was thinking doing. But if there's any questions on example calculations, I can cover those. Were there any questions on calculations? Anything? All right, so we're going to leave thermodynamics for right now. And then we're going to come back to thermodynamics next semester. But the hard thing about thermodynamics is, and what makes it a pain, and people are saying it's very confusing, are all these symbols, QV, QP, delta H, delta U, and what do they mean? And so what happens is a lot of people don't really work at defining them, and then they get into what we call higher level classes, where they already expect you to know that, and then they pile on a whole bunch more, and you're already kind of shaky. What is QV, or what was delta U? What's the difference between delta U and delta H? And so a lot of people are kind of shaky on that, and then they get hit with all these additional ones, because when you get into the next level class, which is straight thermodynamics, then it becomes much more difficult if you don't have the basic ones memorized. And that's why thermodynamics has the highest fail rate out of, I think thermodynamics or organic has the highest fail rate out of organic, because there's too much memorization. A lot of people struggle with memorization, but conceptually it's not that difficult.
So Chem 1B next semester mostly thermodynamics?
Not mostly, just one chapter of thermodynamics in Chem 1B. But it's important. It's important that you try to work to understand this. If you're continuing, let's say if you're continuing in biology, in biochem, there's a lot of thermodynamics in biochem, because they're interested in how much energy you're going to get. So if you have aerobic respiration versus anaerobic respiration, are you going to get the same amount of energy? Okay, how much is the difference in energy? Do you know what the difference in energy between aerobic and anaerobic respiration is? Well, biochemists will. So biochemists are going to do lots of thermodynamic calculations. And biochemists don't use 25 degrees C. Do you know what biochemists use for their temperature? So when you look at the thermodynamic data table, like our Appendix D and our thermodynamic data tables all at 25 degrees C, because it just makes sense to do it at room temperature. But when you look at the biochemical thermodynamic tables, they're none of them are at 25 degrees C. All of them are at 37, yeah. 37 point whatever body temperature is, that's what the thermodynamic tables are. 37.5? Okay, thanks. And so, or if you're engineering, then thermodynamics is going to be all 25, most of the tables. But you'll have tables at other temperatures too, because it depends. If you're working and in cold environments or hot environments, then you'll want thermodynamic data at different temperatures. That's why there's no standard temperature, because biochemists, they probably care a little bit about 25, but it's not very useful for them. All their reactions happen at body temperature. Well, not all, because if you look at reptiles or whatnot. So we're going to come back to thermodynamics, but we left atomic theory, and atomic theory wasn't very useful, because with Dalton's atomic theory, you couldn't predict anything. Dalton said that different elements are different because their atoms are different. And so lead atom's different than a gold atom, but how are they different? Dalton didn't explain. Well, Dalton just said they weigh different amounts, and that's about it. And so Chapter 8 is revisiting atomic theory. Atomic theory is, atomic theory, Dalton's atomic theory was able to make a prediction like the law of multiple proportions, but that's not, enough to predict the difference between gold and lead. And so we're going to come back and we're going to look at the electrons in the atoms. Electrons in the atoms, this is where all the chemistry happens. And so basically, to make the long story short, we're going to replace Dalton's atomic theory with today's theory, atomic theory. Do you know what today's atomic theory is called? Basically, we're going to replace Dalton's atomic theory with quantum theory, or quantum mechanics. It's called quantum mechanics or quantum theory is what we use today. But there's a little bit of history involved in this. And so this is a little bit of the historical development of quantum and then just using quantum. And so we should know a little bit about the history of quantum mechanics. Quantum mechanics was developed in the middle of the last century, mid-1900s. What is that? A neuron or something? Is it? Yeah. I saw an interesting talk about neurons. There's a physicist, this guy was straight physics, not interested in biological systems, and then transitioned to biophysics. This is a guy at UCLA. I went to go listen to his talk, and he has this device where he could listen to the neurons. And the neurons, because they fire electrons, and each time they fire electrons, it gets a click. And so it's so weird because you're listening to somebody's, not somebody, it was a mouse. You're listening to a mouse brain, like clicking, 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 as the neurons are firing. There's a recording, audio recording, if you want to listen to it. Real time, apparently, is what they said, but you can hear the neurons of a mouse brain firing off. They just put this weird hat on the mouse. They didn't do any kind of, or did they? I don't remember exactly. This was a few years back. But we're coming back to electrons. Well, this is electrons and neurons. But we want to know this, and we got redox reactions, we got other types of reactions as well. But basically, we're going to go through some of the history. And light played an important role in the development of quantum mechanics. So we're going to spend some time talking about light. And then we're going to lead to the ideas leading to quantum mechanics and quantum theory. And one of the it didn't go straight from Dalton's to quantum. It went from Dalton's to Bohr theory, B-O-H-R. And then from Bohr theory, it went to quantum mechanics. And so, just for historical context, we're going to look at Bohr theory a little bit. All right, once we have quantum mechanics, then we're going to apply it. And so quantum mechanics, if we're looking at the pattern in the periodic table, can you come up with a hypothesis for the pattern in the periodic table? Because the pattern in the periodic table was developed pre-quantum mechanics. So the pattern in the periodic table was developed in the 1700s by, do you know who did it? Actually, yeah, Mendeleev is usually credited with it, but there's another person that also developed it. I can't recall their name, but this is just based strictly on observations of properties, both chemical and physical properties. And so they group these elements based on their properties. Okay, now we have a pattern. You could observe it as long as you want, and so we could observe the periodic table. Now, can you come up with a hypothesis? This is law of periods, the law of periods. The elements behave this kind of way. And so this is kind of a law because there were some missing elements, and those missing elements were able to be determined. This is not like a rule. A rule, there'll be lots of exceptions. So maybe we need to move polonium from here to there. If that doesn't happen, it's there. So the law of the periods. And then you come up with a hypothesis. Can you come up with a hypothesis for this? Well, people tried and tried, but do you think it's easy to come up with a hypothesis for that, given Dalton's atomic theory? No, it's kind of impossible. So people tried and tried, but nothing came about. And so the development of quantum mechanics came about kind of unexpectedly because the physics at the time, which is Newtonian physics. Newton's physics are like 1/2 mv squared or 1/2 mu RMS squared. the kinetic energy depends on the mass and the speed. So we have an electron. People know what, or maybe could predict what the electron mass is, speed, this kind of stuff. But why did it behave in certain ways? And so, why, when you go from 2 electrons to 3 electrons, do the properties change so dramatically? But when you get back to 10 electrons, the properties go back similarly. So what about that? Electrons are just little particles moving, and we can model that motion using Newton's laws. Newton's laws would be, 1/2 m(u)rms squared. And so there's something else going on that the physicists could not explain at the time. I mean, what's the fundamental description of that? That's the theory. There's no theory for this. And so, like I said, the theory came about unexpectedly, in a way, due to the interaction of light with matter. And so what we're going to do is we're going to first take a look at light and just go through a review of the light, and then we'll look at light's interaction with matter. And so when we look at electromagnetic radiation, these are electric and magnetic fields. These fields, what is a field? Usually a field, when we have an electric field, what we think of in the electric field is we have a positive end and a negative end, and that creates a field. These fields are invisible. And so what happens is if you put something in the field, they'll be attracted to one end or the other. So if you put a negative particle into the field, it's going to be attracted to the positive end and repelled by the negative end. And if you put a positive particle in the field, it's going to be attracted to the negative end. So that would be an electric field. A magnetic field would have a north pole and a south pole. And again, it's invisible, but even though it's invisible, it's going to attract certain things. So the north pole will attract the south pole of an object, and vice versa. But if you have 2 north poles, they repel each other because of the magnetic fields repel. And so these are not static fields. These fields propagate as waves. Well, waves are oscillations like this. And so what happens in an electric field is it oscillates. So for example, the positive end's here, and then as it oscillates, it flips. Now the positive end's on the bottom. And then it flips again, so the positive end's on the top. And so we have these oscillating fields where it's going to oscillate. And so if you're watching this field, it's going to be oscillating plus, minus, plus, minus, plus, minus, as it's propagating. So this is propagating, it's moving here. And it's moving at some speed, depending on how it propagates. And so this is like a wave. Positive amplitude, negative amplitude, positive amplitude, negative amplitude. And so it oscillates. So we have these oscillating electric and magnetic fields that propagate. This is electromagnetic radiation, and that's energy that's being propagated, these fields being propagated here. A wave transmits energy. A wave itself is not matter. And you know this because if you get hit by a wave in the ocean, you can feel the energy of that wave. But a wave in the ocean is different than a wave of light. And so let's talk about that here. One thing is how fast light moves. Do you know how fast light moves? The speed of light. And how fast is the speed of light? About 3 times 10 to the 8 meters per second, or 300 million meters per second. 300 million meters per second is pretty fast, correct? It's pretty fast, but then again, it's kind of slow because, when you see light from the sun, is it instantaneous? Did it hit your eyes immediately when the light was produced? You think? No, it takes time. Do you know how long it takes for light to go from the sun to the earth? Is it 7 minutes? Yeah, okay, 7 minutes. So even though it's moving at 300 million meters per second, it's still going to take a time to travel short distances. But when you flip, well, actually I shouldn't say that. When you flip the light switch and the light comes on the light bulb, is it pretty much instantaneous? Yeah, it's pretty much instantaneous because the distance is so short and light moves at the speed of light. So when it's being generated in the light bulb like this and it hits your eyes, it doesn't take any time to get to your eyes. It's so fast. And then when we look at that light coming from the light bulb, that's oscillating electric and magnetic fields that are hitting your eyes. And when the oscillating electric field hits your eyes, you know, it's plus, minus, and there's things in your eyes that are either positive or negative. And what's that going to do? Well, if there's no field there, you know, they're going to do nothing. If there's a static field there, let's say you have a negative and something in your eye that's negative, it's going to be attracted to the positive, right? But if you have an oscillating field, what's going to happen? When this light hits your eyes, then whatever you have in your eye will start to oscillate with the field. This is like if you have a little buoy. If you have a little buoy, the buoy is going to oscillate, right? The buoy is going to be oscillating in a wave, an ocean wave, because the waves are going up and down. Well, now we have these electric waves that are going up and down, and then you have something that's got some kind of charge on it in your eye, and that's going to start to oscillate with the field and go up and down. And so that's going to be a transfer of energy from the light to your eye. We can feel this with infrared. So I said we can't see the infrared, but you can feel the infrared. And the way you feel the infrared is you bring your hand close to it. And when you bring your hand close to it, then you're going to feel the infrared waves. And the infrared waves are oscillating electric fields. And your hand's got molecules and stuff, water, and those are going to start to oscillate with that. And it's going to, your hand's going to get hot, right? Feeling the infrared. You don't want to touch the object because then too much heat transfer. But if you go by a hot object, you can feel the heat coming off, and that's heat's just oscillating that. And so we're very interested in how the electric fields interact. People are worried. Some people are more worried about the magnetic fields. You know, so a lot of people have, including friends of mine, have these electromagnetic radiation detectors. Have you heard that? So they go around and they look at the microwave, computer, lights, you know, outlets, electrical system. They're looking for, you know, harmful electromagnetic radiation. So I used to work with a lot of magnetic fields. And so one of the, you know, General Electric used to manufacture one of the things I use, and they had a T-shirt that they gave away to everybody, and this T-shirt said, "Oh, there's no ill effects from electric and magnetic fields." And then they had this cone head person, you know, like on a cartoon character saying that. But some people are saying the magnetic fields are more dangerous to biological systems than electric fields. Of course, people who are looking at this are very interested in this because, you know, maybe they can use it to kill things like cancer cells. You know, so maybe they could use the magnetic fields to kill cancer cells. Might be very effective. The sign that measures peak to peak? Oh, this one? Oh, the distance here? That's called lambda. Lambda is the Greek, that's a lowercase lambda, the Greek alphabet. And this lambda is referring to wavelength. Wavelength.
You said they kind of oscillate with each other?
No, what we're looking at is we're looking at the oscillating electric field, plus, minus, and how that interacts with matter. So let's say you have a radio wave. You know how fast radio waves travel? So if somebody's broadcasting, let's say in Los Angeles, do you hear them pretty much instantaneously, or does it take, is there a time delay? This is a short time delay? Okay. But it's not very long because radio waves move at the speed of light. And so radio waves are moving at the speed of light, and they're oscillating electric fields. And then they used to have these car antennas that were made out of metal. Have you ever seen those? You know, vandals would try to break off the metal antennas and get some kind of kick out of that. You know, so there used to be a lot of broken antennas back in the old days. But So they developed car antennas that you can push down into the fender, and then when you wanted to drive and listen to the radio, you pull out the car antenna out of the fender, and it'd stick out like this far or something like that. Some people had huge antennas because they wanted to get better radio reception. But let's say it broke, and then, you know, the antennas are kind of expensive. So what people would do is they put a clothes hanger, metal clothes hanger, into the slot where the antenna goes, and it would work, you know, because it's metal. But what if they tried to put a plastic or wood hanger in there? Would that work? No, it didn't work. And so it wasn't the clothes hanger, it was because it was metal. That's why it worked. So any metal would work. Nowadays, the antennas are a lot smaller, because they have amplifiers that can amplify the signal, this kind of stuff. But anyway, getting back to this, why? Why metal? Well, metal has lots of loosely held electrons. So if a radio wave comes along, electrons are negatively charged, what are they going to do? They're going to start oscillating with the radio wave, right? And then that's going to create this oscillation, which you can measure, and that's going to give you your sound, you know, music from that, because the wave itself is going to carry the information regarding the sound. The wave is just a composite of all the different frequencies in there.
So does that mean that like, matter emulates the waves of
Yeah. And they do something called resonate. Have you heard of the resonance? They'll just resonate with it. So metals can easily resonate with radio waves because the electrons can easily be excited. We call it exciting the electrons. But plastic, the electrons are too tightly held, and so they won't resonate. So the radio wave hits it and does nothing to it because the electrons aren't moving. You know, they're stuck. They can't move.
That doesn't have anything to do with conductivity, does it?
Yeah, it does.
It does?
Yeah.
But, okay. I thought that's not only when it's touching. That's not only when two things are directly touching.
No, usually things with loosely held electrons are conductive.
Yeah.
So, for example, you could possibly use graphite to make an antenna because graphite can conduct electricity and it has loosely held electrons. But the problem with graphite is it's what we call an anisotropic conductor. It only conducts in one plane. It's not a three-dimensional. Three-dimensional would be an isotropic. Metals are isotropic. Doesn't matter where you measure it, it's going to be the same or should be the same. Whereas graphite, it does matter how you measure it, what the electrical conductivity is. But anyway, things with loosely held electrons, like metals, can oscillate with radio waves. So anything with loosely held electrons will make a radio antenna out of. So it depends on how this. So you might try to excite the electrons in a metal or plastic clothes hanger. What would you do? Well, one thing you might try to do is increase the power. If you increase the power, you're increasing the amplitude of this. So you're making a tidal wave, let's say, you know, versus a small wave. But the weird thing is that even if you increase the power, the electrons don't oscillate. They don't resonate at that frequency. It has to be the right frequency, let's say. So if I had a plastic clothes hanger, it's just not resonating with it. And so increasing the power isn't going to do it. But you got to be careful because increasing power can cause damage, though, because if something just absorbs a little bit, then it could be very damaging. And so we have lasers. Like when I worked in the laser lab, you know, I was always scared because one mistake could mean that you're blind. Because let's say if you're working with an infrared laser and it hits your light, I mean your eyes, the light hits your eyes, you know, your eyes are toast. You know, they aren't going to be able to reverse it because the damage is already done. And so, you know, you wear special goggles, but what if you forget your special goggles, you know? Or what if they're up here and you didn't realize they're up here and then some laser gets off the mirror and then hits your eye? You're screwed for life, you know? So I you know, going into the laser, I didn't work. I did just some, but I didn't really work much in the laser lab. You know, you got to adjust the mirrors and do all this other stuff to get the laser beam pointed at your sample, and then you take some measurements. Um, so that always scared me. And I didn't want to pursue that. So didn't do much beyond a few experiments. But we were working with infrared lasers, which would cause blindness. But you could, so powerful lasers, you got to worry. And infrared light's absorbed by your flesh quite easily. There's lots of ways to absorb infrared. You got lots of water molecules in your eye. So those water molecules start vibrating, can absorb lots of energy, cause lots of damage. So what we have to do is we have to change something, not the amplitude, we have to change this, the lambda. And the light moves at the same speed no matter what the lambda is. And so over here we say up here it's slowly oscillating, down here it's quickly oscillating. And that quickly oscillating we describe with frequency. That is how many peaks pass by you in a second, peak to peak. And so how many of these we call wavelength. How many wavelengths pass you by in a second? That's called a cycle. One wavelength that is down, up, back to the same place is a cycle. And one cycle per second is called 1 hertz. And so we're looking at the frequency in hertz, cycles per second. And so this is going to have a lot more cycles per second. And so in order to excite the electrons in a plastic coat hanger, we don't increase the amplitude, we have to increase the frequency. Because eventually, those electrons will start to oscillate with the frequency and then get excited. For plastic, do you know what frequencies will cause that oscillation to happen? Around what we call, we describe light based on its wavelength and frequency. So let's take a look at that here. Uh-huh.
So when do you know, like, if something like matter is going to be like, easily excited by the electrons? Like, how do you know when to increase amplitude versus increase?
We concentrate on just the frequency. How you know is only the frequency. The amplitude will cause a lot more stuff to happen, but it has to resonate. So I could increase the amplitude all I want. It's like this is a little bit different, you know, in certain ways. It's like how boats might interact. You know, if you have a tiny boat, then it's going to be hit by the waves quite easily. And so a tiny boat's going to be going up and down. But let's say you had a gigantic boat. Is it even going to feel these tiny ripples? No. And even if you increase the amplitude, it still doesn't feel those. You have to change the wavelength, you know. We could increase, if they're really tiny ripples, you know. Well, we can increase the amplitude, but the frequency just doesn't really interact with the boat. So the boat, you know, can just plow through those waves. Well, it's kind of the same thing here. We're interested in the frequency and the wavelength. So we can have the frequency here. The units of frequency are cycles per second. But nobody ever writes cycles. Everybody just writes per second. Which is a hertz. And so we're looking at hertzes here. You know, this is called megahertz. Megahertz radiation is like, have you ever tuned your radio to an FM radio station? I don't know if people listen to radio, but you know, they would have, okay, we're at 100 megahertz or 99.9 megahertz. Have you ever heard that? Yeah, this is the frequency. So this is radio waves here. Or if you have AM, if AM, then it's a little lower frequency. AM radio is in the kilohertz range. And so they say, oh, we're at 1,000 kilohertz or 999 kilohertz or something like that. 1,000 kilohertz would be 1 megahertz. But anyway, we'll have FM out over here, and then AM radio here. And then we have higher, they have these higher frequency radios, but you need a special license to use those. Have you heard of the ham radios and that type of stuff? The police and the fire use. But a lot of those are restricted. Military uses them as well. So there's certain frequencies that aren't.
So to reduce noise.
Hmm?
Is that to reduce noise?
The restrictions on the frequency? Yeah, to reduce noise and chit chat. You're not supposed to go on those frequencies. Some people listen to those frequencies, but they have these police scanners and they can listen to what they're talking about, but they can't broadcast on those. It's restricted. I'm sure there are other frequencies that are, not only restricted, but they probably code the communications, encrypt it so that people can't listen. What happens if you put a metal in a microwave? Have you ever done that? If you put a metal in a microwave, what happens?
It's gonna explode. It's gonna cause fire.
Yeah, you get sparks. You get sparks. Why? Because the electrons get, you want to excite the electrons, but you don't want to excite them too much. If you excite the electrons too much, what's going to happen? The electrons are going to get so excited that they get knocked off the metal atom. Right? They do something called ionization. And so the wavelengths here, when you look at the wavelengths, 1,000 meters. 1,000 meters for radio waves. 1,000 meters, that's 1 kilometer. And so if you have a 1 kilometer wavelength, that's the distance from peak to peak, and it's coming at you at 1 million cycles per second. That's like 1 million kilometers per second. It's huge. So these are moving very fast. So anyway, so we can characterize this stuff. If you put it, okay, so radio waves, what do the radio waves do? Radio waves excite electrons in metals. But if I put my wood or plastic coat hanger in the microwave, is the plastic or wood coat hanger going to give off sparks? No. It might get warm, it might not, but usually what microwaves do in the context of chemistry is these cause rotations. What's easier to do, to rotate a water molecule or to vibrate a water molecule? What do you think is easier to do? Rotate. The vibrations are like this, so you're fighting against positive and negative attractions, whereas rotation is just rotating the molecule like this in space. So water molecule is negative on the oxygen end, positive on the hydrogen end, and if you flip the field, you flip the molecule. You flip the field again, you flip the molecule. So it causes rotations, the molecule. So this causes small molecules. The molecules have to be polar. Small molecules to rotate. Maybe they don't. And so usually when people talk about microwave spectroscopy, they're looking at rotations of molecules. So if you hear like NASA's doing some microwave spectroscopy, they're looking at what kind of small molecules there are out there. And based on how much energy it causes to rotate, they can tell, is that water or is that some other molecule? And so microwave spectroscopy we can do. You need more energy to vibrate water, and so that's infrared. This causes vibration. So infrared vibrations. Both rotations and vibrations are kinetic energy. So both of these cause the temperature to go up. And so you don't want to be hit with too much microwave, otherwise you're going to get kinetic energy that is, your kinetic energy is going to go up. This is great for cooking food. So if we can rotate the water molecules, it's going to cause kinetic energy, and it's going to result in temperature rising. You know, it's kinetic energy and temperature are directly proportional. And we can cook it. We can also cook food using infrared. A lot of people like this. You know, when you have red hot coals, they're emitting a lot of infrared as well. And the infrared can cook the food as well. So people like this for cooking too. And so this causes vibrations. Infrared is right on the other side of red. This is visible. Visible light is just a small part of what we call the electromagnetic spectrum. So this is the EM, electromagnetic spectrum. So we're going from low energy on the right to high energy on the left. So what's higher in energy than infrared is red light. And so infrared is just on the other side of red. The wavelengths of infrared are in the micron region. Usually, for certain things, we look in terms of frequency, like radio waves, we look in terms of frequency. Microwaves, we do too. If you look at your microwave oven, it's probably at 4.5 gigahertz or 5 gigahertz. Your cell phone, too. Your cell phone is in this, usually in the microwave region, the gigahertz region. Some people, you know, worry about that, the radio waves and the coming off your cell phone. And so my sister got me a Shield phone case. She said to use it. But it's so bulky. I haven't used it yet. But it was a gift to prevent from too much exposure. My sister has one of these gauges too. But I have friends that are very particular about it. But anyway, this is vibrations. It causes visible light causes electron excitations. So let's say you had colored coat hangers. If you had colored coat hangers, why you see the color in the coat hanger is because of visible light exciting electrons in matter. We have the rainbow of colors, which we divide into red. What's this color called over here? It looks like orange.
Still red.
Red orange.
Look on the left side on the projector. Do you think it looks really orange?
No. But you know, yeah. Like you know, some people when what do they say? Where was I? I was in Japan, and they have the stoplights there, so it's just red, yellow, green. But everybody kept saying blue. And it's blue. Well, to me, it looked green. So to avoid this, people put numbers on them. And so if I really want to know what is it, then I'm not going to try to describe the color. Instead, I'm going to describe it by its wavelength. Because then it doesn't matter what color people see. The wavelength is simple. And so this is why I memorize. You know how I memorize this? I memorize the wavelength of 760 and 390. And the units are in nanometers. Nanometers, this would be 760 times 10 to the minus 9 meters. Or if you don't want to memorize it to this level, you just memorize it from 400 to 800. You know, that's another way you can, you know. But I know the electromagnetic spectrum. Not everybody can see all the way to 760, and not everybody can see to 390. There are lots of people who don't see this at the very edges of the electromagnetic spectrum. And then there are people that might even be able to see further into the, you know, beyond the limits here. Definitely certain animals can see beyond those limits. Uh-huh.
So we're going to have to like learn how to do the calculations with lifetime.
Yeah. Well,
Like some numbers that we have to memorize.
No. You just have to use the equation. I'll give you the equation. I don't expect you to memorize the equation. And the numbers. The speed of light I'll give you. The speed of light we call c. And I'll give it to you to 4 sig figs. Uh-huh.
So would 400 and 800 in a calculation be accurate enough, or would you want us to do it with 390, 760?
400 and 800 is enough.
Okay.
400 and 800, because all we do is we just kind of estimate where it is. So let's say I told you I have 1,000 nanometer light. Where is it?
Beyond red.
Beyond red is called
I do not know.
infrared.
Okay.
Infrared. 1,000 nanometer light is 1 micron light. Infrared's usually done in microns. And so that's the only reason you need to know. And then do you know what's on the other side of violet? What that's called?
With the X-rays and then.
No. Right on the other side of violet is called ultraviolet. We can't see ultraviolet, but let's say I had 300 nanometer light. If I had 300 nanometer light, where do you guess it's going to be ultraviolet? That's the only reason you'd know it. Because let's say you have a light bulb that's emitting 300 nanometer light. Would you, unless you're like doing tanning or something like that, you wouldn't want to stand in front of that. In fact, I think that's how I damaged my eye. My vision used to be quite okay, 20/20 or something. And then when I went to grad school, my vision just went downhill. I had to start wearing glasses because everything was blurry. And then I think I figured out why, because I was making a lot of photocopies. Photocopies emit a lot of UV light, and I wasn't using any eye protection or anything like that. It was just, and I never closed the lid because I was copying books and journals. And so I would spend every day I'd spend hours at the photocopier just being blasted by the light.
Like, how is that different than just being outside?
It's the same. It's the same. Like a lot of because I used to be outside all the time, but a lot of my friends that were outside as they're getting old, they're having cataracts and other eye damage. You wouldn't believe they aren't that old, but they've had a lot of eye damage from ultraviolet light. You should wear sunglasses, but because down the road, and sunscreen too. I never wore sunscreen. I should have. Sunglasses. Definitely do sunglasses because it's a surprisingly large percentage of older rock climbers have eye problems and skiers and snowboarders.
Does blue light hurt your eyes, like you said?
Yeah, so they say blue light's damaging to your eyes. So you should, because this excites your optic nerves too much. The blue light causes some damage. And so violet and blue light are the higher energy ends of visible light. And so like the monitor, I have, you can buy monitors where you can adjust the output. And so you can reduce the blue on the spectrum. On some monitors it's quite blue. They want a whiter light. So. Or you could buy blue blocker. Have you heard of those blue blocker glasses? That will filter. Those just filter off a lot of UV and blue. Fortunately, they don't emit much UV. UV would be more damaging than blue. But yeah, it kind of surprised me how many people are. My sister, who who pretty much lived most of her life in Jackson Hole, Wyoming. She just had to have her lenses replaced, as a lot of her friends did too, live in Jackson. I guess it's pretty common there, the high elevation and then the ski type thing. So they're totally into skiing.
Now, so there's snow bounces a lot of light back.
Oh yeah, the albedo. Yeah, the snow. I when I was in the Boy Scouts, we went on every year we'd go on the High Sierra backpack, and the High Sierra backpack, we went over one pass there, and I didn't bring sunglasses, because I didn't think of it. It's like I think I was in 9th grade, and I got snowblind, and snowblind, I couldn't see. My eyes hurt so much, because we were going over a pass. So the pass was totally snowed over, so we spent like 2 days on the snow, and yeah, it was a very painful experience. It was, so after that, yeah, I was always very careful in the snow. So when I go, like say I go up to the snow and I see people without sunglasses, it's a bright blue day out, I think, man, serious eye damage. That was before, the other thing, we have two big environmental things. One is that gets a lot of media attention. One is the global warming and CO2, and the other is the ozone. The ozone is due to, CFCs, chlorofluorocarbons, damaging the ozone layer. And there has been significant damage because, you don't have to go outside for very long to get sunburned now. It used to be you could be outside all day and not get such a serious sunburn. And so definitely the ozone has been damaged.
I have a question. Why is it like 760 times 10 to the negative 9? But like in the visible spectrum, it seems like it's between, like, it's more around 10 to the negative 7. Based on this, right?
Yeah. That's because 760 times 10 to the minus 9 is equal to 7.60 times 10 to the negative 7 meters. So we just moved the decimal point 2 over. So if we make this number smaller, then we can make this bigger.
I understand that.
Yeah. And so it is 7 times 10 to the minus 7, so it's in the 10 to the minus 7 range. But people don't like decimal points for some reason. So people hate saying 7.60 times 10 to the minus 7. Everybody wants to say 760. That way we don't need any decimal points and we get 2 decimal places of precision. Does that make sense? And so this is why they use nanometers. This is why the other unit here, 10 to the minus 10 meters, is called an angstrom. So when we get to X-rays, if you look in the X-ray spectrometer, they measure it in angstroms. How many angstroms is the wavelength? But people are getting away from angstroms because you'd have to do the same thing. You have to use decimal points. And so rather than using angstroms, now they're using picometers. How many picometers is your X-ray? And then let's say you had 1.23 angstroms. If you have 1.23 angstroms, that's 123 picometers. And so it's easier to say 123 than 1.23. Maybe. And so it's just a matter of convenience using the particular units that we're doing. So if let's just say this area, red spans kind of a wider range, so maybe I was a little bit too. And so we have lots of different shades of red. Too premature with the orange. Let me move the orange over here. And so that was red, and then we'll put the orange maybe here. What do you think? 650. Okay, we'll go here. We'll put orange there. And then after orange, what color does that look like? That kind of looks like yellow. And then after yellow looks green. And then after green, blue. So there are different shades of green, different shades of blue. And then purple, but we don't call it purple. You know what we call it? Violet. But between this, I don't know if you could tell, but between violet and blue is another color. Indigo. I don't know why. Actually, I do know why. But I do know why because of the artist's color wheel and for making predictions. And so I would just say blue to violet. And the other reason why is because of the mnemonic Have you heard of Roy G. Biv? Red, orange, yellow, green, blue, indigo, violet. And so this is a Roy G. Biv here. And so this gives us an easier way to memorize the rainbow of colors. One of the reasons is to have a nice symmetric color wheel, like this. This is the color wheel. Roy, and then G is on the other end, and then Biv. Do you see how nice and symmetric that is? And we use this color wheel for doing different things. And so let's say a leaf, like green leafy vegetables or leaves on plants, they're green. And so we might ask, why are leaves and green leafy vegetables green in color? And so one of the things could be, the reason it could be green is all the other colors are absorbed away. And so let's say, you shine the rainbow, because white light from the sun, we get the entire rainbow of colors. And when you shine the entire rainbow of colors, what colors interact with the matter? And so it depends on the molecules and whatnot that you have in there. And so one of the things that could happen is you absorb all these colors and all these colors, and the only thing that's left is green. And so you eliminate all the other colors of the rainbow, so that's why the green leaves are green. Because if it absorbs all the colors, if it absorbs or reflects all the colors, what color it would be?
Black and white.
If it absorbs all the colors, we call it black. Because it just looks black, it absorbs all the colors, the rainbow. If it doesn't absorb all the colors, let's say it reflects all the colors, or the white light just passes through it without interacting at all, then we call it colorless or white. And so that's what we see. But there's another way we could get green. Do you know the other way we could get green? Actually, there are multiple ways we could get green. And this is why there was a big push. You heard about the red diode? The red LEDs have been known for a long time. So there's lots of red LEDs used, and green also. So we had red and green LEDs. And so at the traffic signals now, they have LEDs, which are a lot brighter, like little lasers. But they couldn't make all the colors. And so if you had red and green, you can't make all the colors. We need one more color to make all the colors. And do you know what color that was? Blue. So if you had red, green, and blue, you can make all the colors. How can you make all the colors? You mix those three in different proportions, and then you can get all the colors in the rainbow. Well, there's another way we can produce green, and that's by absorbing red. If we absorb red, then we get all the colors add up to green. But anyway, I'll stop here because I'm done.